Okay, hello everyone. In the previous lectures, we learned about gray box testing method, including mutation-based fudging and the generation-based fudging for effectively finding software bugs or effectively increasing code coverages. So in this lectures, we will learn the techniques for automatically fixing software bugs discovered by various software testing methods we have learned so far. For reference, researches for automatic program repairs are relatively recent and a little more active compared to the research for software testing. Okay, let's start with this week's lectures. So in today's lectures, I will motivate you by answering the following questions. Why do we need automatic program repair techniques, which is APR techniques? And after motivating you at a high level, I will classify APR techniques into the two main approaches, which are general purpose program repairs and special purpose program repair techniques. The key difference between the two techniques is whether the technique focused on fixing any kind of error or on fixing a specific error types. In particular, today I will focus on special purpose program repair techniques. So I introduce one of the state-of-the-art techniques for fixing memory deallocation errors such as memory leak or use after free or double freeze. Okay, let's start with the motivation of these automatic program repairs. As you might have already guessed, debugging accounts for half of the total time for software development. The figure on the right shows that it takes on average of 200 days to properly fix a single bug in a commercial softwares. In this box plot, the x-axis represent the commercial software names and the y-axis represent the bug fix times. And as you can see, the box plot also shows that about 50% of bugs in both commercial software are fixed within 10 or 100 days to the 300 days. And some outlier bugs in the PostgreSQL takes over 1,000 days to fix. This is the first reason we need automatic program repair techniques. Second reason is also obvious. The number of software vulnerability increases rapidly every year. This graph shows the number of CVs for each year. For example, in 2010, the number of CVs was about 4,000, but in 2050, that number had been risen to about 6,000, and in the last year, that number had risen to about 18,000. That is the second reason we need to the APR techniques is that the number of software bugs keeps increasingly every year. Third, manually fixing software bugs such as double free errors and null pointed reference is time consuming and error prone even for experienced developers. More specifically, even if the software developers has fixed the bugs, the developer cannot be sure whether the error has been fixed correctly or not. This is because commercial software usually consists of hundreds of thousands of lines to millions of lines. It is also very challenging to fix a single bug. Moreover, unexpected new bugs would be introduced while fixing the original bugs. For example, the code below is a simplified example where on actual bugs, the double free error occurs in the Linux kernels. To fix these single double free errors during a 1 year, the developer tried to generate 3 different patched programs, and 3 other developers reviewed these patches. And this interesting real-world example will be discussed in detail later in these lectures. To summarize why the automatic program repair APR techniques are needed, the number of software bugs is gradually increasing, and fixing each bug in the real-world software usually takes a long time, like 1 year. And finally, manually fixing it is very challenging. This is why the APR technique is needed. So APR techniques have received an increasingly amount of attention from both industry and academia in the last decades. At a high level, we can classify these techniques into the 2 approaches: general purpose program repair and special purpose program repairs. First, the general purpose repair techniques are in principle able to repair any types of the errors. However, because this technique is generic, so it may have poor performance in fixing certain types of errors. On the other side, the special purpose program repair techniques focus on fixing the specific kinds of errors. So it does not generic technique, but it is highly effective for fixing the certain types of errors. First, let me explain the general purpose program repair techniques. This technique usually relied on the test cases, whether the generated patches are valid or invalid. So this generate and valid approaches is one of the main general purpose repair techniques, which consist of 2-part patch synthesizers and patch validators. This technique first takes a buggy program and tries to generate candidate patches from the predefined patch space, such as add free statement or remove the free statement and so on. And then the patch validator checks whether this generated candidate patch is valid or invalid by using the set of test cases. So if all the test cases pass successfully, this technique considers this patch have been fixed the error. If there are test cases that fail, the patch synthesizer generate a new candidate patch again, and the validator verify the new one again. So in other words, while repeatedly performing patch synthesis and the verification process, if the technique generates a patched program which accepts all the test cases, this approach returns the patched program as an output. Okay, on the other hand, the special purpose repair techniques specialize in the specific errors. And as you can see, certain classes of the errors include memory deallocation errors, or null point reference, or pub overflow or integer overflow, and so on. For example, a tool named leakfix specializes in fixing memory leaks safely without introducing new errors, while vfix aims to repair the null point reference errors. So in this lecture, I will focus on one technique, namely memfix, which is automatically fix various memory deallocation errors. First of all, let me explain the 3 types of the sum error memory errors, which are memory leak and use after free and double free errors. These errors occur when dynamically allocated objects are not deallocated properly in the program languages like C and C++. More specifically, the memory leak error occurs when the programmer may forget to deallocate an object P. And the use after free errors occurs when the programmer may deallocate the object P too early, even before it is used. And lastly, double free errors occurs when the program may deallocate the object P more than once. So these errors such as memorily ML and the double free DF and user after free UAF are one of the most troubling errors in the C programs. This table below shows that these are prevalent in the popular open source software project. These bugs are even more common than buffer overflow and the integer overflow. For example, the number of memory deallocation errors in the Linux, about 6,000, where this number is bigger than the number of both buffer overflow and integer overflow. Moreover, each of these errors should be carefully examined and fixed, because otherwise these bugs become significant source of serious security vulnerabilities. For example, these series numbers below are the partial list of the vulnerability that occurred due to the user after free at this year. So first, I will explain how the developers manually fix the real errors in the Linux kernels. Then I will explain how the API technique automatically fixes these errors. Let me briefly explain the simplified this code. Briefly, at line 1 to the line 5, two objects, out and in, were allocated and used and got deallocated properly. And at line 7 and 13, the buffers in and out are reallocated with the increased size 2 respectively. And when these buffers in and out fail to get reallocated, these buffers will return null respectively at line 7 and at line 13 respectively, and go to the error handling code at line 12, which deallocate the buffers in and out. So in this code snippet, there exists two double free errors. I will give 20 seconds, so look for the bug trace yourself. Okay, did you find the bug trace? Okay, I will explain the bug trace. The first trace is as follows. When the buffer in at line 7 fails to get reallocated, it goes to the error handling code at line 12. And then in this handling code, the free statement is called on the buffer out that is already deallocated at line 4. And this is the first double free errors. Similarly, when the malloc at line 13 fails, the buffer in is deallocated twice at line 50 and the 21s. Okay, now we understand how the two double free errors occurs. So the next question is, how do we fix these errors? Can you guess or imagine how to fix these bugs?